Okay, here we're going to do a calculation involving finding a force, an electrostatic force acting on an object. There's nothing particularly hard about this calculation, but it is going to be a little bit long and time consuming. So here's our situation here. We have a 5 microcoulomb object at point A, so that's there. And we've got a 4 microcoulomb and a negative 2 microcoulomb, and we have all these distances. So what we want to do is we want to find the force acting on this little particle here. And I find when I'm doing these questions, it's useful, excuse me, to think of myself as standing at the particle that I want to find the force for. Now the first thing I have to do here is just a bunch of geometry. So the first thing I need to do is find the actual distance between these two and between these two. And I also need to find these angles. I'll call that theta and that alpha just to keep them straight. So let's find this distance here first. We're going to use the Pythagorean theorem. So this is the hypotenuse. So we're going to recognize that the hypotenuse is equal to the square root of the squares of the individual sides. So 8 squared plus 18 squared. And that works out to be 8 squared plus 18 squared equals square root answer 19.7 centimeters. And here, similarly, 8 squared plus 12 squared, that's h. So 8 squared plus 12 squared, square root answer, I got 14.4. So that's 14.4 centimeters. Okay, so that's the hypotenuse or also the radius. Okay. And I also need those angles. So I'm going to use the tan. Tan theta is equal to 8 over 18. So theta, 23.9 degrees, or 24 degrees basically. And tan alpha, which is 8 over 12. So alpha is going to be 8 divided by 12, inverse tan, 33.7 degrees. Okay, so now with all of that in hand, I'm going to erase this so that I can work underneath here. I'm going to go ahead and find the magnitude of these forces. Remember, according to Coulomb's law, that F is equal to K, Q over R squared. So I'm going to do the 4 microcoulomb force here. And I'm going to have the same formula for the negative 2 microcoulomb force. So this is like this interaction. That's what this is. And this one is this interaction. Okay? So 9 times 10 to the 9. Q, 4 times 10. Remember, microcoulomb means 10 to the negative 6. Divided by, I can't put that radius in centimeters. I got to make sure I convert it into meters. So 19.7 centimeters, of course, is 0.197 meters. So all that in hand, 9 exponent 9 times 4 exponent negative 6 times 5 exponent negative 6 divided by 0.197 squared. I got 4.6 over here. And now I'll do the same thing, but for the other one, the other pair. Notice as I do this that I'm not going to bother with the sign on this charge. The sign on this charge is just going to give me a sign in this equation. And the sign in this equation simply represents direction. And for me, I'm going to do these basically looking for the magnitude of this force. And then once I get to the end, I'll take a look at the diagram and I'll go back and I'll interpret the directions using the law of electrostatics. I find that's a lot simpler than trying to follow all of my negatives around in the equation. So let's make that 0.144 meters squared. Again, remembering to convert this to meters because we can't use centimeters. It's not a standard unit. So here I got 4.34. I mean, that makes some sort of sense, right? Like this charge, the first charge was bigger than the second charge, but the second charge was closer, so those two sort of balance each other out, and the two forces end up being pretty similar to each other. Now, this is a positive, this charge right here, and this is a positive up here. So looking at it from the perspective of where I'm at, or the charge that I'm looking at, I'm repelled by that 4 microcoulomb charge. That means that my force is going to go up and away as a repulsion up here. Or, if I consider that direction, x, and this is going to be the same angle as this angle down here, so x, 24 degrees y, right? X, 24 degrees y. Similarly, although sort of the opposite here, I have 5 microcoulombs, negative 2 microcoulombs. So again, considering my law of electrostatics, instead of being repelled here, this force is going to pull that object towards it. Opposite charges here attract, and again, I'm looking at it from this particle's perspective, so I'm getting pulled in here. This is 33.7 degrees. So if I'm looking for this angle and I imagine the Z pattern, then this is going to be 33.7 degrees as well. Or I could call that x, 33.7 degrees negative y. So now I've got the force, and with both its magnitude and direction produced by those two charges, now I have to find the sum of those two forces, or the total force that's acting on this object. So I got 4.6 xy, so x then y, 4.6, and the angle at the beginning was 24 degrees. And here I go x then negative y, the angle at the beginning is 33.7 degrees, and I got 4.34 here. So that's my opposite, so it gets my sine, so this is 4.6 sine 24, 4.6 cos 24, 4.6 sine 24 is 18. Whoa, let's try that again. Oh, 4.6 sine 24 is 1.87. That makes a little bit more sense. Newtons in the y direction. 4.6 cos 24, not 20, 24, is 4.2. Newtons in the x direction. Similarly here, this is my opposite, so that's my sine, 4.34, sine 33.7, 4.34, sine 33.7 is 2.4, and 4.34 cos 33.7, that's what this one is, right? 4.34 cos 33.7, the adjacent side, is 3.6 newtons. So now I can sum in my x and y direction separately. In my x direction, I would have 4.2 newtons from my first force, and I would have 1.87 in the y direction. For my second force, I would have 3.6 newtons in the x direction, and careful, this is in the negative y direction, so negative 2.4 newtons. Taking the sum of those things, I get 7.8 newtons, and here I got 2.4 minus 1.87, 0.53 newtons, and that's negative. And finally, I get to recombine my components to come up with my overall forces. So 7.8 newtons, minus 0.53 newtons. So my resultant here, using the Pythagorean theorem, again, h is equal to the square root of a squared plus b squared. So 7.8 squared plus 0.53 squared. 7.8 squared plus 0.53 squared, square root that, 7.82. So my total force would be 7.82 newtons. And to get my direction here, my theta, x, negative y, I'm going to use tan theta, is equal to 0.53 on 7.8. Where's tan at? 3.9 degrees. 3.9 degrees. So there you go. It's long. There's nothing particularly challenging about it. You got to start with the geometry, get the angles and the distance between them. Once you have that, you can do the magnitude and you can interpret the direction using the law of electrostatics. Once you have two forces, you can use components to add them. And that then is the total electrostatic force that would be acting on that particle from those two particles combined.